Hello, this is your lecture video for section 14.1 and a couple more sections in 14. All the topic is factoring. The first thing we're going to do is just make sure we understand what factoring is. Do you remember maybe way back in elementary school when you would see something like this and you would create a factor tree, and you might say that that's 2 times 8, and then you would be done with the 2 because you can't factor that any further, but the 8 you could factor that and say 2 times 4 and you'd be done with the 2, but the 4 can go again and that would be 2 times 2. And so you'd end up saying that 16 is equal to 2 times 2 times 2 times 2, or if you used exponent notation, you would say 2 to the 4th. This process is called factoring. So what is a factor? If we have 2 times 8 equals 16, these numbers are factors. So it's numbers that get multiplied together to create a product. If we were asked to list all of the factors of a number, list the factors of 48, I'm going to list these in pairs so that I make sure I get all of them. So 1 times 48, what would be the next pair of numbers that multiply to 48? 2 times 24. Can we divide 48 by 3? And here's what I'm asking. 3, 4, yes, we can. So 3 times 16. How about 4? 4 times 12 would be 48. 5 doesn't work. And I'm using my divisibility rules, by the way, that we learned in a previous section. 6 times 8 is 48. And then 7 doesn't work. And if I try 8, yes, it does work, but I already have that pair. So I have all of these factor pairs. So this is the list of the factors of 48, all of the numbers that will divide evenly into 48, or all of the numbers that 48 are divisible by. 48 is divisible by. When we're asked about a greatest common factor, that means the biggest factor that all of the list of numbers would have in common, the largest number that divides evenly into all of the integers that we're being asked about. For example, if the question is, what's the greatest common factor of 12, 18, and 30? It's asking what's the biggest number we can come up with that will divide into all of these numbers. So one way we could do this is to list all of the factors of 12. So 1 times 12, the next pair would be 2 times 6, 3 times 4, and we have all of the factors of 12. The factors of 18, 1 times 18, 2 times 9, 3 times 6, 4, no, 5, no, 6. Yeah, but then we're repeating again. So there's all the factors of 18. Factors of 30, 1 times 30, 2 times 15, 3 times 10, 4, no, 5 times 6, and then we'd start repeating the list. Okay, so now that we have listed all of the factors of these numbers, what's the largest one that appears in all of the lists? So they all have a 1, but that doesn't really count because that doesn't really do anything. They all have a 2, so that's a G. That is a common factor. They all have a 3. We're getting bigger. Is there something even bigger? They all have a 6, and that's the biggest factor that they all have in common. So the GCF would be 6. Okay, so that's one way to find the GCF. It takes quite a bit of time to list all of the factors of multiple numbers. We're going to use, let me see something. Let me show you a different method. Give me just a second. Do we have that coming up? Well, we just did that example, so I'm going to go to the next one. 24 and 40. Yeah, I'll keep it the same. Those are two numbers. It won't be too bad. 1 times 24, 2 times 12, 3 times 8, 4 times 6. Those are all the factors of 24. 40 would be 1 times 40, 2 times 20. 3 doesn't go into 40. 4 does. 4 times 10, 5 times 8. What is the greatest factor that they all have in common? 1 will never really count because everything has one in common. They both have twos, they both have fours, they both have eights, not 12, 10, 20. Okay, so 8 is the GCF. If we're dealing with variables, and we have, let me expand this just to show something. That's x squared times y to the fourth and x to the fifth times y to the third. How many x's, x times what do they both have? They both have an x squared. If I think, well, this one has more x's, yes, it does, but this one doesn't. So x squared is the biggest that they both have. This has y to the fourth. This has y to the third. The most that we can get out of both of them would be three of them. This has three. It has another one, but this one doesn't have that extra y, so they don't both have it. And for it to be common, they both have to have it. So x squared, y cubed would be the variable parts for these GCFs. What rule can we follow when we're finding a GCF with the variables? If you notice, x squared and x to the fifth, we ended up using the 2. Y to the fourth and y to the third, we ended up using the 3. So what rule can we follow? It's going to be the lowest exponent of the variable, which makes sense because if they both have to have it, it can't be bigger than one of them. They both have to have it, the factor. Find the GCF for these 3 terms. So we'll deal with the number parts, 12, 24, and 18. Is that the same one we did up here? Nope, that's a different one. Okay, 12, 24, and 18. 12 is 1 times 12, 2 times 6, and 3 times 4. 24 is 1 times 24, 2 times 12, 3 times 8, and 4 times 6. And then 18 is 1 times 18. By the way, if you just kind of are really good with your multiplication facts, you don't have to write all these out. I am showing every possible step. Sometimes you can just see what it is. That's even better, just showing all the work. So what is the biggest factor that they all have in common? 2s, yes, they all have 3s. They don't all have 4s. They do all have 6s. I think that's the biggest one. So the GCF would be 6. A to that we have a 6, a 3, and an 8. And we're going to use the smallest of those exponents. So a to the third. B to the, there's a 1. This is like having no b's, b to the 0 and b to the 2. The smallest is b to the 0. So that means b is not even part of the GCF because they don't all have a b. Remember, they all have to have it in order for it to be common to all of them. C to the 13, 9, and 4, we use the smallest one because that's what they all have. So this would be our GCF. Factoring is the reverse process of multiplying. So back up here, factoring is when we go this way. If we were to multiply all of these 2's together, we would get back to the 16. So factoring is the opposite of multiplying. So factoring is kind of dividing. We're going to use the distributive property to factor out the GCF from a polynomial. Kind of like we're going to undistribute it. What would it have looked like before the distribution would have happened? So instead of like going this way, we're going to look at it this way. We're going to start off with an expression and we're going to factor it so that it looks like 2 factors being multiplied together. So what is the GCF for 8x and 20? So for 8 and 20, the biggest factor that they have in common, they both can be divided by 2. Like if I stuck these numbers 8 and 20, they both can be divided by 2. Can we go bigger? Yep. What, they can both be divided by 4. Is there anything bigger they could be divided by? No. So 4 is the GCF. And do they both have an x? No. So x cannot be part of the GCF. So the GCF on this one is just a number. It's 4. And I want to write this a specific way. So we're taking 8x plus 20, and we're going to factor it. So I'm going to write the GCF right here. And then I'm going to open up a set of parentheses, and we're going to write what it would have looked like before the 4 got distributed. So 4 times what would have given us this 8x term? It would have needed to be 4 times 2x, because 4 times 2x would give us 8x, and that's what we have right there. So 2x, and then plus 4 times what term needs to be written right there to get us to this 20? What would have been there? And that would need to be a 5. So, and we can check by multiplying. 4 times 2x is 8x. 4 times 5 is 20. We have the same expression. We're saying these two things are equal. It's just one, this is factored because it's written as a, in this case, a monomial times a binomial, but two polynomials being multiplied together versus just having the terms written out. So final answer is this. We're going for the factored form of this expression. Another example. Okay, we have 3 terms, so the GCF needs to be common to all 3 of those terms. So looking at the numbers, 9, 27, and 18, 9 is the greatest factor that they all are divisible by. I'm going to write this a certain way. 9 and x to the 1, 2, 3. We take the lowest one, which is just x. So 9x is the GCF. And we're going to end up having 3 terms in here. What would this have looked like before we distributed the 9x? So 9x times what gives us 18x cubed? That would need 2x squared. If you're struggling to get this number, here's really what we're computing. We're taking this 18x cubed, and we're dividing it by the GCF. So 18 divided by 9 is 2. X cubed divided by x is x squared. So if you're, you can think about it, let me do the next one. You can think about it in terms of multiplying or dividing. Let's look at the next one. Minus what needs to be written here. I think about it in terms of multiplying. 9 times what is 27? 3. X times what gives me that x squared? X. But if that's not working for you, you can take the 27x squared divided by your GCF of 9x and then simplify that and you'll get the same thing, 3x plus, this would be 1. 9x times 1 would get us back to that 9x. Okay, so our answer is this. This is the factored form of this expression because it's a monomial. It's 2 polynomials that are connected by a multiplication. It's like we're doing that factor tree. We're not done there, but we're getting to a point where we take a number and we break it apart into its factors, and that would keep going, but you get the idea. Ooh. Factor the GCF from this expression. So we have 10, 45, and 15. They all are divisible by a 5. So that what we're writing outside of the parenthesis is the GCF. Variable part, they all have x's. We've got x to the 4th, x to the 3rd, x squared. The smallest would be x squared. Then we have y's, y to the 3rd, y squared, y to the 1. So that would be y to the 1. What would be left in the parentheses? Because we're starting off with 3 terms, we will have 3 terms after we divide by this monomial. What would be left would be 2x squared y squared. And you can double check me by multiplying these two. Make sure you get back to that 10x to the 4th y cubed. And I'm double checking, yep, plus 9x y minus 3, and I don't need any variables here because I already have the x squared y, so just multiplying by 3 there. Factor out the GCF. 9b cubed, 4c squared, 9 and 4, there is no GCF other than 1, but 1 doesn't count because it doesn't, everything has a factor of 1. B cubed and c squared do not have a common factor. When that happens, there's no way to factor it. We would say prime. That would be like back in the day if you were trying to do a factor tree on 17, you couldn't because it's prime. It's not 2 times something or 3 times something. There is no factorization of prime expressions. Okay, the next one, I'm going to skip that one. Let's keep going. The next section, 14.2, is factoring trinomials. So 3 terms, and they're of the form, so we'll have an x squared term, an x term, and then a constant term. Let's see. How do I want to do this here? I'm actually going to skip here. I'm going to skip all of this and just go to some examples and teach you some things as we go. So x squared plus 13x plus 36. Before we do that, I want to recall with you how we multiply, like let's say we are multiplying x plus 2 times x minus 4. Do you remember that we would take that x and distribute it? That would be x squared minus 4x. And then we'd take that 2 and distribute it. And then we would combine these terms, so x squared minus 2x minus 8, and then that would be our expression. So that's multiplying, but now we're going to go backwards and we're going to take this expression and write what it would have looked like before it got multiplied. And I'm going to teach you something called the AC method. So this, in standard form, this is called standard form when we have it written as ax squared plus bx plus c. So our a is 1, our b is 13, and our c is 36. So we're going to take a times c, 1 times 36, and our b is 13. So a times c, and this is b. We're looking for 2 numbers that multiply to 36 and add to 13. So factors of 36, 1 times 36, 2 times 18, 3 times 12, 4 times 9, 6 times 6. Which one of these pairs would add to 13? Let's see. Yep, there's one. The 9 and the 4, that can make a 13. So that tells us if we have x plus 9 times x plus 4, I'm using these 2 numbers as in my binomial terms, x plus 9 times x plus 4. Let's check if that multiplies to this original expression. And let me get some more space here. Well, okay, so let's multiply x plus 9 times x plus 4, and we're checking. That would be x squared plus 4x plus 9x plus 9 times 4 is 36. Middle 2 terms are like terms. 9 and 4 is 13 plus 36. That's what we were working with. So we know that this is the factored form of this expression. And that's what we're doing. We're factoring. We're taking an expression and writing it in factored form, what it would have looked like before it got multiplied. Let's do another one. So off to the side, I just want to make sure you're seeing this. A is 1, B is negative 16, and C is 63. So we multiply A times C. So for us, that's 1 times 63, so that's 63. And our B is negative 16. So we're looking for two numbers that multiply to 63 and add to negative 16. So 1 times 63, 2, nope, 3 times 21, 4 doesn't go in there, 5 doesn't go in there, 6, 7 times 9, and then we start repeating factors. Which pair of numbers could we get a negative 16 out of? And I'm seeing this, and here's what I'm asking. We can adjust signs to be both positive, both negative, or one of each. Can we create a negative 16 out of one of these problems? Yes, we can. This one would produce a negative 16 if we were adding. So we know the two numbers we're looking for are a negative 7 and a negative 9. So we're going to come back over here and make one factor a minus 7, a minus 9. And that's it, but we're going to double check. So a times a is a squared. This is us checking. A times negative 9 is minus 9a. Negative 7 times a is minus 7a. Negative 7 times negative 9 is positive 63. Middle two terms are like terms. And we can see that if we check, we get right back to where we started, which is what we want when we check. We want to make sure that we've made an equivalent expression. So just to be clear, this is your answer. It's asking for this expression in factored form. And let's look at another one. These can take quite a bit of practice till you see the pattern. Once you see the pattern, you're going to see it. And it just takes a lot of practice. So be patient with yourself and keep working these examples. So we want it in standard form or descending order, which means we need to rewrite this. So if we write it in descending order, the p squared comes first, and then the p to the 1, and then the constant term. So this is the order that we need to be working with it in. And then we come over to make this chart, a times c, two numbers that multiply to a times c and add to b. This chart, that's your gold. You're going to use that for every problem. Make sure that's somewhere very clear in your notes. May even put that on the sheet that you get to use for the final. That's how this problem happens. All right, so for us, a times c is 1 times negative 40, so that's negative 40, and b is negative 3. So we need two numbers that multiply to negative 40 and add to negative 3. 1 times 40, 2 times 20, 3 times, nope, 3 doesn't go into 40. 4 does go into 40. 4 times 10, 5 times 8. There it is, if we can get the signs right. So I'm going to write all of the possibilities, both negative, both positive, one negative and positive, and then the other way. Which one of these, if we are adding or subtracting, gives a result of negative 3? It's this one. So that tells us that the numbers that we need to be working with are a 5 and a negative 8. So we're going to come back here and make one of these a positive 5 and one of them a negative 8. And you can double check, but that will get you back to the original expression. So this is our factored form. What if the trinomial has a greatest common factor? That needs to come out first. So on this trinomial, 3x squared plus 9x minus 12, all of these have a 3 in common. So if we factor that 3 out, what would be left is x squared plus 3x minus 12. It's kind of like if we go back to this example and we say 18 is 2 times 9, we're done with the 2 because that can't be factored any further, but the 9 can factor some more like this. The 3 is done, but this might be able to factor again, and we need to check that. So our next job is to just keep this 3 here. It's part of the problem, but it's done. And we're going to take this, and I'm going to do some scratch work off to the side, and get what those factors are. So factors of a times c that add up to b. So a times c is, for us, our a is 1, b is 3, c is negative 12. So a times c is 1 times negative 12, so negative 12 adds up to 3. So what two numbers multiply to a 12? 1 times 12, 2 times 6, 3 times 4, and then we start repeating. Which pair of these can we add and get a 3 out of? I'm not seeing anything. 1 times 12, 2 times 6, 3 times 4. None of those work to get a 3 out of. So that means this part is not factorable. We actually were done right here. And let me just double check my works. Take out 3, that's x squared plus 3. Oops, I made a mistake right here. That's not a 12. Okay, let me start over. My apologies, and it's okay for you to see me make mistakes because that's part of the process. So no problem. Let's do it again. If we were in class, you probably would have caught that and saved me some time, and it's okay. We all, it happens. Okay, so when I factor out a 3, x squared plus 3x minus 4, that's the part that I missed last time. So we keep that 3, it is done. But this remaining trinomial, we need to see if that is factorable. So we're going to set up our chart, a times c, two numbers that multiply to a times c, and add to our b of 3. A times c is 1 times negative 4 is negative 4. Our b is 3. So 1 times 4, 2 times 2. And this one could be either way. So which pair of these could we add and multiply to negative 4 and add to 3? So if I try, let's try this one. And I'm going to consider all cases, both positive, both negative, one of each, and then switch it one of each. Trying to add these and get a positive 3, this one would give me a positive 3. So the two numbers I'm looking for are negative 1 and a positive 4. And so my factors would be x minus 1 and an x plus 4. If you're going to check this, I would recommend multiplying these first, and then you'll get this, and then you can multiply by the 3, and then you'll get back here. And it'll work. Let's see, how many more do we have? Okay, I'm going to leave you there, and let's go to the next section. 14.5, factoring the difference of squares and perfect square trinomials. So we actually dealt with this in a couple sections ago. We looked at it as a special pattern. Remember that we called these conjugates, and we noticed that when we multiply conjugates together, the two middle terms will cancel. And let's just see how that plays out. X times x, x squared. X times negative 4 is minus 4x. 4 times x is plus 4x, and then 4 times negative 4 is minus 16. Those two middle terms are like terms, so we combine them, and in this case, they cancel, so we're just left with x squared minus 16. And the next one, same example. So that'd be 9n squared plus 21n minus 21n, and then minus 49. Those two middle terms are going to cancel, and we'll just have that first and last term. Same thing would happen here. I'm just going to skip that example and keep going. So these, to summarize these two, we're going to look at a rule that's called the difference of squares. Difference of squares means that we're going to start off with an expression like this, and we're going to end up writing it as the product of its conjugates. To help you recognize when you're dealing with the difference of squares, the word difference in math means subtraction, and the word square in math means that it's a perfect square. So you might see that exponent of 2, but you might not see the exponent of 2 because some squares, well, it's important to recognize numbers that are perfect squares. Like 1 squared is 1, 2 squared is 4. Let's take that list and create it. 1 times 1, 2 times 2, 3 times 3, 4 times 4, 5 squared, 6 squared, 7 squared, 8 squared, 9 squared, 10 squared, 11 squared, and that list keeps going. But these are perfect squares. Oh, missed that. You can fill in the list, but there it is. List the next 4 perfect squares. So if we have, this one is x times x, that's x squared. This is x squared times x squared, that'd be x to the 4th. Remember, we add the exponents. X to the 3rd times x to the 3rd is x to the 6th. What is x to the 4th times x to the 4th? That'd be x to the 8th. And if we kept this list going, we would get something like this. And we can summarize that and say, anytime there's an even exponent, we have a perfect square. So let's just practice recognizing what is a perfect square. 36, so is 36 in this list? Yes, it is. And is this exponent even? Yes, that's a perfect square. 10 is not in the list, so that's not a perfect square. 49 is in the list, but this is an odd exponent, so that's not a perfect square. 121 does not divide evenly by 25. Oh, wait a minute. The square root of 121 is 11. The square root of 25 is 5. So that actually is a perfect square, kind of hiding out there. Yes, this is a perfect square. 9 is in the list above, and that's the even exponent. So yes, 4 is in the perfect square list, even exponent, but not an even exponent. So that's not perfect square. Perfect square, perfect square, perfect square. Yes. So when we see, we do actually have the pattern of a perfect square subtracted by another perfect square, then we use this perfect square factoring. So we set up our parentheses. This first term gets square rooted or factored in that first position. From the formula, one's a plus and one's a minus, and then this gets square rooted in that second position. So square root of 49 is 7. You can see that these form conjugates, x plus 7, x minus 7. If we were to check this and multiply, we know that the minus 7x plus 7x, that cancels, and we'd just be left with that last term, which matches what we were working with. Is this a perfect square pattern? So what we're looking for, is this a perfect square? Yes. Is this a perfect square? Yes. And is it a subtraction sign between them? Yes. If those 3 things are yes, then it follows the pattern of being the difference of perfect squares and will factor like this. So this is going to factor as 6x, one's plus, one's minus 5. Next one, is it a difference of perfect squares? Yes, that would factor as 2p and 2p. One is plus, one is minus, and then 3q. If you want to just double check, remember that you can multiply. Those 2 middle terms should cancel, and you should be left with that original expression. Okay, this one. Is it a perfect square? Yes and yes. How do I know that 16 over 49 is a perfect square? Because both of these numbers are perfect squares. So let's see what that would look like. So the square root of w is w, one's plus, one's minus. What is the square root of 16 over 49? Well, square root of 16 is 4, square root of 49 is 7. So one of these is plus 4/7, one of them is minus 4. Oops, 4/7. This one, is that the difference of perfect squares? No, because there's no minus sign. So when it's a plus of perfect squares, we can't use the difference of squares formula because difference means subtract. if this would have been x squared, n squared minus 64, we would be able to factor that as n plus 8 and n minus 8, but with that plus, different problem. So if we have the plus of perfect squares, not factorable. Okay, we're going to combine some things here. So we always want to first check, is there a GCF? If there is, we're going to do that first. Let me give you something. Let me give you sort of a flow chart that you can use to help you factor. So any type of factoring, you always want to try the GCF first. So let's do that. They have a 2 in common. That is the GCF. After we factor out a 2, that would leave x squared minus 25. And then we're going to count the terms of what's left. If it's 2 terms, we're going to try the difference of squares. If it's 3 terms, we're going to try the AC method. So we have 2 terms left here, x squared minus 25. Is that a difference of squares pattern? Yes. So this 2 just gets recopied. And then we're taking this x squared minus 25 and factoring that by using the difference of squares pattern. And so this is our final factored form. So sometimes a problem will have a couple different kinds of factoring methods used in it. And that's why the directions say factor completely. Like, don't just factor and say, I'm done because I did something. You're getting there, but there's still more to be done. So don't stop factoring until it can't factor any further. If you have x to the first exponent, you can't factor any further because we're not going to break apart an x. It could be done. We're not going to do that. So just know if you hit an exponent of 1, you're done factoring. If you have an exponent of 2, you might still be able to factor a little further. Factor completely. So is there a GCF? Yes, there is. Let's get that out first. So 3p. So that would leave 9p squared minus 1. If I'm going too fast, just pause the video and catch up. It's okay if you need to pause and rewind. You do it until it makes sense for you. And then we're going to count the terms. Here's 1, 2. So if it's 2 terms, I'm going to try the difference of squares. If it would have been 3 terms, we would have tried the AC method, trinomial. Okay, 2 terms. Is this a difference of squares? It's a minus sign and a perfect square and a perfect square. Yes, it fits the pattern, which means we can factor this further. So we're going to say this is 3p, just recopying. And then 9p squared minus 1. If we apply our difference of squares form, that would be 3p times 3p. 1's plus, 1's minus, the square root of 1 is 1.